Hey onliners, this is conservation of potential energy, maybe around lab 13 if I'm not mistaken. So this, you need the apparatus of this spring that came in your kit. You gotta be very careful not to overstretch the spring. These springs are very sensitive. So I recommend that we don't go over 1 kilogram so that we keep the spring from going crazy. If this spring stretches so far that it doesn't come back, you have to go to the hardware store and get yourself another spring somehow, okay? So come on in and let me show you what I did was I taped a meter stick over here and then I used the clamp from your ticker tape timer, the thing that was holding it. And so then the spring gets hanging right from the little twisty thing, all right? And then I put a meter stick. Now, you probably might only have half a meter stick. It doesn't matter as long as you tape the meter stick down far enough so that you'll have numbers throughout the entire range of this lab. So if I look at 1 kilogram and 1 kilogram stretches my spring, and again, each spring might be a little different, but 1 kilogram stretched this thing about 10 centimeters. So as long as you have a meter stick hanging somewhere, somehow, so that you can take readings in that range of about 10 or 20 centimeters, I think you're gonna be okay, all right? So you understand the apparatus? 1 spring, 1 ticker tape timer, clamp, and then all the masses that we can muster up. All right, so this lab actually would only take 35 seconds to do if we knew, and now I know you're reading the book, so I know ahead of time that you know what this word means. The spring constant, that force constant of the spring, is the ratio between the force that makes it stretch and how much it stretches. Hooke said that the force is directly proportional to the stretch. So if you pull twice as hard, it stretches twice as far. I can't believe he got his name in the book for this one, all right? Let's try that again. If you pull a little, it stretches a little. If you pull a lot, it stretches a lot. So when you read the book, you realize that's called Hooke's law. And this K, this spring constant, is the ratio between the force that made it stretch and how far it stretched. Now, I could put this on here and just pull and then measure how far it fell, but how far it stretched, but I'd have to know how hard I pulled with. So unless you have some kind of force meter, you don't really know how much you pulled with, but you do, you have a spring scale. So you could do this lab, I'm gonna tell you not to, but you could do this lab by pulling it with a spring scale and reading the force on the spring and then measuring how far the spring stretched. You could, but there's a better way. Why not use planet Earth to pull, okay? This thing is a kilogram. How much does it weigh? 9.8 newtons. This is a half a kilogram. How much does it weigh? 0.5 times 9.8 is 4.9 newtons. So in a weird sort of way, you could have planet Earth pull for you. So here's what you do. See if we can zoom in right over here and see where this is when there's no mass hanging on it. I think it says about 29 point something here, okay? So just trust me on this one. I'm looking right at the end of my spring before the loop, and it looks like it's right on 30, okay? So let's say 30 centimeters is my 0 mark. So when you read your lab handout, it'll say 0 it. Well, for us, 0 might be 30. Now you could work really, really hard and put a piece of cardboard here and tape the meter stick in such a way where it says 0 right there. If you want to do that extra effort, that's fine. Do it. Then 0 is really 0. But I'm going to say 0 is 30. And it doesn't really matter because I don't care about where it is. I care about how much it's stretched. So with a half a kilogram on there, I'm looking at it. It went from 30 to 39.6. So I'm writing down in centimeters how far it stretched when I put 4.9 newtons of force on it, okay? Repeat with a kilogram. Now remember, don't go over a kilogram because I don't trust these springs. But if you pull with a kilogram, Hooke's law says it should stretch about twice as far. And it went from 30 to about 51.2. So that's pretty close to being double, okay? go back up here like this. If you did it right, it'll go back up to 30. If you killed your spring, it won't go back to 30. That's when you go buy another spring. So here's what you do for part 1. Do as many data points as you can by combinations of masses, okay? So you got 100, you got a 200, you got a 500. Make every combination you possibly can and write down how much it's stretched by. Fill in that table as much as you can. The more data points you got, the better your lab is, because then you can really make a nice graph. So full-size graph of, and listen to this, what depends on what? Does the stretch depend on the force, or does the force depend on the stretch? So the answer is, on the y-axis, you have delta y, the displacement, and on the x-axis, you have the force in newtons. Make sure it's newtons and not mass, because mass is not what we're graphing. If you graph that, and you know Hooke's law, you know the slope of that line is going to be 1 over the spring constant. So see how you can get the spring constant from this lab? So all that I just described was an intro that you need to do to get K. Why do you need K? Because you read the book, and you know K is in the equation for the potential energy stored in a spring. 1/2 K times y2 squared minus y1 squared. And y2 and y1 is the 2 positions it's at. Okay? So here's the scoop. This is the actual lab. Take a mass. Let's do a 1/2 kilogram just to make sure I don't break any springs here. And hang it down here like this. And this is how long the real lab is going to take. You lift it up. Now remember, my reference point is the end of the spring. You could pick here if you wanted, but it's better if you pick the same spot you had at 0. Okay? Because then from 30 to here is y1. So I'm going to lift this up in the air. All right? And some people actually videoed it with their phone just so they can see where the numbers are, because they were having trouble seeing it in real life. But you lift the mass up, and then you let it down. Don't go all the way up. Don't go back up to 30. Just go up a little bit, let go, and then read that number, that number, that number, that number, that number, that number. Read the top number and the bottom number, top number, bottom number. That would be y1 from 30 to that one, and y2 is from 30 down to the lowest point. In other words, just read those 2 numbers, the high point and the low point. y1 is the highest point, y2 is the lowest point. What do you get from that? Well, now you can do 1/2 K, so yeah, that's why you needed K, times y2 squared minus y1 squared. Now remember, it's the difference between 30 and that one. If you put a 0 here, it's one less step I got to do. I have to subtract whatever I read from 30 to get the actual y1. So don't write down 32, it's 2, right? The difference between 30 or your reference point and where it ends up. So here and here is y2 and y1. All right? Write those 2 numbers down. If you subtract those 2 numbers, you get h, the height change. Now think about this. What kind of energy was lost as it fell? And the answer is gravitational potential energy. What kind of energy was gained when you let it drop? It lost gravity potential, but didn't it gain kinetic for a little while? But then at the very bottom, it lost all that kinetic also. So what's all the energy turning into at the bottom? Spring potential energy. So the name of the lab is conservation of potential energy, because effectively, if you ignore the middle kinetic, you're just converting some of the potential energy gravitationally into spring potential energy. And that's all we're out to prove. So the loss in gravity potential energy should be exactly equal to the gain in spring potential energy. Is it going to be exact? Oh, no. But you're going to try your best and analyze it and discuss, okay? Again, it's a mini lab. Just fill out and answer all the questions in the lab, in addition to a little bit of theory, okay, with maybe a sketch of the apparatus and the equations that we're going to use. And then in the discussion, remember the results. Tell me what you did. Just pretty much that table is the results. And then with a discussion, discuss the results, discuss some of the reasons why we have some error, and the last one is how could we improve it, okay? So that and answering the questions in the lab is all you have to do, all right? So let's just summarize. First, you find the spring constant from this full-size graph by changing and doing as many mass differences as you can and measuring the elongation versus the force pulling. Then, when you got K, put a mass on there, lift it up, and read the top number and the bottom number, top number, bottom, top number, and the bottom number, okay? And then switch masses and do it with a different mass. Now, I caution you, when you have the 1 kilogram mass on there, don't pull it down too far because then the force at the very, very bottom is tremendous. So be very careful at the bottom to just lift it up a little. Don't go crazy and let it fall like crazy or you'll break the spring. So I recommend something like that for the 1 kilogram mass. So again, maybe you do 500, 700, and 1,000 as your 3 trials, okay? And that's it. Hopefully, from this lab, you're going to learn the conservation of potential energy. All right, go to it.